Hey everyone, welcome back to the channel. So in this video, we'll be looking at question 8 from February-March 2024, question paper 42. However, I'm going to skip 8A and B Roman 1 and 2 because those are basics questions that they usually ask in almost every paper, the number of neutrons, energy released, or the definitions. So let's look at something a bit interesting today, which is Roman 3. Where they ask the isotope xenon-142 is unstable, the isotope xenon-132 is stable. Suggest a reason why xenon-142 is unstable. Okay, one way to explain this is using binding energy. Because we know when we draw this graph, I believe all of us are familiar with this. This is binding energy per nucleon, and this is nucleon number. X-axis is nucleon number. So the graph looks something like this. Yeah, something like that. Yeah. And this one is Fe56, which is iron 56, one of the most stable elements. So if we were to plot xenon-142 and 132 on the graph, what will we get? So xenon-142 is definitely somewhere here, because this is increasing number of nucleon number, right? So 142 is definitely greater than 132. So 132 will be somewhere here. So based on what we have plotted, we can deduce that xenon-132 has a greater binding energy per nucleon compared to xenon-142. So the greater your binding energy, that means the more stable you are. Why? Because binding energy means energy needed to separate the nucleus into its individual nucleons, like nucleons into like protons and neutrons. So you have greater binding energy per nucleon. That means your nucleus is really stable. You need a lot of energy to actually break them apart, to actually break the nucleus apart. But if you have a very low binding energy per nucleon, that means your nucleus isn't that stable. You don't need that much energy to break it apart. You just need a very less energy. So, in conclusion, the greater the binding energy, the greater the stability of the nucleus, and vice versa. But unfortunately, the answer scheme didn't mention anything about binding energy per nucleon. They talked something about neutrons. But speaking of binding energy per nucleon, this explanation is not wrong. It's also another way to explain on the stability of nucleus. Just that for this particular variant, the answer scheme wrote a different answer where they talk about neutrons. So let's say we have a nucleus with us here. Inside a nucleus, we know we have protons and we have some neutrons as well, right? So these protons in the nucleus carry a positive charge. So what happens when you put positive charge and positive charge together? They will repel. Same thing in the nucleus. So when you have this positive charge in the nucleus, this will lead to a strong repulsive force, causing the nucleus to fly apart. That is why we have neutrons. These neutrons are neutral, so they are not going to add into the electrostatic repulsion. They're actually going to help to ensure the proton repulsion is controlled, or you want to say in other words, to counteract the proton repulsion. There is a force that is responsible for holding protons and neutrons together, and that is actually something called a strong nuclear force. It is one of the 4 fundamental forces of nature. So that is why we have neutrons with the protons together inside the nucleus. If you only have protons, the nucleus is going to fly apart. So we have neutrons to counteract the repulsion. We also have the strong nuclear force that holds both proton and neutrons together to ensure they do not break apart. Okay. Now, in general, the neutron to proton ratio for a lighter nuclei is roughly 1:1. Okay, a generally balanced or a stable nucleus has a balanced neutron to proton ratio. So for lighter nuclei, I say it's around 1:1, while a heavier one tend to have more neutrons than protons, but not too much. It has more neutrons than protons because a heavier nuclei means you have a higher number of protons as well, right? So if you have a higher number of protons, you need a higher number of neutrons as well to counteract the proton repulsion. Am I right? Yes. But there is a limit. Having too much of neutrons, excess number of neutrons in a nucleus can disrupt the stability of the nucleus. Why? Because, okay, let's talk about energy. For example, we know that electron has an energy level, right? Okay, this is energy. So what happens is electron at a very high energy level will go to the ground state, which is a lower energy level, to become more stable. So what happens if you have too much of neutrons but very less protons? It's the case where you have too much of proton, very less protons. Now, I said just now it becomes less stable. Why? Because this will force the neutrons to go to a high energy level, making the neutron less stable. Okay, I'm going to draw a barrier here to show that this is proton and this is neutrons. Because proton energy level cannot jumble up with neutrons energy level, right? They have their own required respective energy level. So let's say we have 2 protons and we have 10 neutrons inside the nucleus. So we have 10. So what do I mean by force the neutrons into a higher energy level, making them unstable? So here's the thing. The nucleons here are at a very, very high energy level. They can't go down to a lower energy level to become more stable because the next energy level is fully occupied. If you think that the neutron can actually jump to this energy level, no, it can't. Because like I said, this particular portion is reserved for proton energy level and this particular portion is reserved for neutron energy level. So is there something that I can do to make the neutron more stable now? Not neutron, sorry, the nucleus more stable now. Yes. There's something called beta plus decay. So when a nucleus has way too many neutrons, it can undergo beta plus decay to reduce the neutron to proton ratio. So this process actually involves beta plus decay is where the neutron is converted, not converted, I wouldn't say converted, is transformed to a proton while releasing an electron as well as anti-neutrino. So now this neutron here, for example, I said this neutron is transformed to a proton. So now it has become a proton. Therefore, now it can come to this energy level because it is now a proton. If it's a neutron, no, you can't come because like I said, this is reserved for proton. So, this is why you undergo radioactive decay. Because when you have an unstable nucleus, you undergo radioactive decay to become more stable. So, now what if I have too much of protons? Just now I said, okay, too many neutrons. Now what if I have too much of protons? Will that make my nucleus unstable? Yes, it would make your nucleus unstable. Because when you have too much of proton, you have a very, very high electrostatic repulsion, which will naturally cause the nucleus to fly apart or basically break apart because you have a very high electrostatic repulsion. It will start to repel each other even more. So now, is there a way to make it more stable? Yes. This time, you have to undergo beta minus decay. Beta minus decay, you transform proton to neutron. So when you transform your proton to neutrons, you are slowly reducing your electrostatic repulsion. And when you transform proton to neutron in this decay, you will also release positron as well as neutrino. Beta plus decay, you release electron and anti-neutrino. Beta minus decay here, you release positron and neutrino. Okay, so now after all this, how does it relate to the question that we want to do. So, xenon 142 here has 88 neutrons and 54 protons, whereas xenon 132 here has 78 neutrons and 54 protons. Number of protons are the same because they're isotopes. And you can actually look at here. 54 protons is in the question actually. Okay, so xenon 142 has quite an excessive number of neutrons, you know. So in this case, the issue is too much of neutrons. So that is why it is very unstable, because you have too many neutrons. If let's say the question asks, so now how can we make xenon 142 stable? You do beta plus decay. You mentioned that xenon 142 has to undergo beta plus decay. If it's too many protons, you undergo beta minus decay. If they ask. If they did not ask, just say too many neutrons. This would also be an acceptable answer. Talking about binding energy will also be an acceptable answer. The reason I discussed this particular question is because of the answer scheme. The answer scheme did not mention anything about binding energy. They talk about neutrons. So it's basically another perspective, another point of view. And best part, all this just for 1 mark. Yeah, Cambridge is really nice, right? All that just for 1 mark. Okay, xenon 142 decays into isotope cesium-142. Okay, the sample initially contains only nuclei of xenon 142. After a time equals to 6 seconds, the ratio is equal to 31. That means if I were to write this, it's 31 over 1 lah. Yeah. Then they ask us to calculate the half-life of xenon 142. Show your working. Okay. So, if they say after a time equals to 6 seconds, the number of undecayed nuclei of xenon 142 is 31. Not undecayed, sorry. Number of decayed nuclei of xenon 142 is 31. And undecayed is 1. That means originally, or should I say initially, it was 32. Right. Initially, the sample contained 32 nuclei of xenon 142. Because after 6 seconds, 1 nuclei has decayed and it has left 31. 31 nuclei is left to decay. So that means initially, my sample had 32. Right. So we have this formula, n equals to n naught e negative lambda t. Lambda is basically your decay constant, t is your time. So, and n naught is basically the initial number of nuclei. And n is basically the undecayed nuclei. So, if I were to write this in the equation, I'll get 1 equals to 32 e negative lambda 6. 1 is my undecayed nuclei of xenon. 32 is my initial number of nuclei of xenon 142. Not 31, it's 32 initially. Because this one, 31 is after 6 seconds. After 6 seconds, 31 decayed. And 1 is the one that is left undecayed. That means initially, I had 32. So, here, I write 1 because n here means undecayed. N naught is initial. So, undecayed is 1. And initially, I had 32. So, if you do the math, 1 over 32 equals to e negative lambda 6 ln 1 over 32. I think you're going to get a negative value if I'm not mistaken. So take your calculator, type ln 1 over 32. So you get around negative 3.4657 equals to negative 6 lambda. Yeah, it's a negative value, right? So these two negative can be cancelled out. Then divide negative 6. You get lambda equals to 0.5776 2, 3. Oh, also, I know you might be thinking why I'm taking such a long number, because in between calculation values, make sure you take more than 2 significant figure. If it's your final answer, you want to make it into 2 significant figure, it's fine. But in between calculation, try to take it more than 2 significant figures. Okay, so now we have find lambda. What can we do next? So we know there's a formula, half-life equals to ln 2 over lambda. Right, so now that is what they're asking, they want to find half-life. So half-life equals to ln 2, where lambda is 0.577623. Make sure you write the correct value from your calculator, don't copy wrongly. So I divide, I will get perfect answer. Just nice, 1.2 seconds. And this is your final answer. Okay, so the common mistake right in this question falls at this part. Here and also here. Instead of writing 32, you might write 31, because they give you equals to 31 and straight away sub inside 31. But no. So this is where you should read the question carefully. They said after time equals to 6, the ratio that has decayed is 31 and undecayed nuclei is 1. That means initially before even a decay happened, you had 32 nuclei. Yeah. So that is why you must put 32 here instead of 31. Yep. So I hope you understand how to do this question. Gives you a better idea on how to approach it. I wish you all the best for your physics paper 4. I know it's this Friday. I hope everything goes well for you. Just stay calm. Okay, just stay calm. Just breathe in, breathe out, and I think you'll do just fine. Okay? Alright. All the best, and make sure to stay hydrated as well. And take care. I'll see you in the next one. Bye bye.